Is now starting. All attendees are in listen-only mode.
All right, so thank you everyone for coming, and thank you to Ray for giving this presentation. For everyone that's tuning in, just wanted to introduce Dr. Ray Weiss, 2017 Nobel Prize winner in physics. So I don't want to spend too much time introducing him. He's going to talk a little bit about gravitational waves and eventually talk a little bit about what he's interested in our coatings for, and why he's so interested in looking at our silicon coatings. So with that, I'm going to hand it over to Ray to go ahead and get started.
Thank you very much for having me. I mean, it's a pleasure to be here. I have to tell you, everything that's happened has been just wonderful. You know, it's rare you walk into an environment where it's so friendly, so fast. That's really just delightful. Anyway, I want to give special thanks to Nick Snyder, who was the guy who listened to my nonsense on the telephone, and then he turned it over to Jesse Bishop, and found out that I wasn't completely crazy, but only a little bit. And now then we have a new member of this group. It's Corey Robinson, who helped yesterday. So thank you, all of you. And I have yet to meet the rest, but anyway, it's a great place, I have to say. A really pleasure to be here. Now, my talk is what is the name of the talk is a new field that has been started by a lot of people. And that's why I say it's on behalf of the LIGO collaboration. Now we'll see if this wonderful thing that has been set up for me works. And let's see if it goes to the next slide by going forward. Well, let's do that. And there we go, wonderful. Now, this slide is the people who made it happen. And I want to point out to you somebody that's not too far from you. Let's see if I can get the cursor to work. Where is it? There you go. Good. Thank you very much. Whoops, I lost it again. Oh, it's a very sensitive cursor, but it's getting there. Look at this place. It's called Penn State. It's right down the street. And they have a big group that is in this thing. They are contributors to this field in an interesting way. They may not have built it, but they were deeply and are deeply involved in the data analysis. And there's a large group of people there, very good people, and they intend to continue into this thing that I'm about to tell you about. But before I get to that very end point, I want to tell you a little about the field and a little bit about the science, okay? And I'll keep looking at you. If you look like you're falling asleep, I'll go faster. Okay. Anyway, so let's see how it can. So the very first thing I want to say is, what is a gravitational wave? But before I do that, I have to explain to you why that such an idea even has to exist. Now, all of you learned Newton's gravity well, probably in high school and maybe even in college. But at Newton's gravity, there is just a very, very simple thing. It's a beautiful theory. It works for everything that we deal with. And the big advantage that it gave the world was that when Newton put that thing together as a theory back in the 1600s, it explained something that was going on in the heavens, and namely the orbit of the moon around the Earth and the orbit of the Earth around the sun. It was all quite natural development. And it also explained, allegedly, how apples fell out of trees. And that was a big step forward. It was the universality of science that worked both on the Earth as well as in the heavens. And that was not something people had done before. I think that's a more important development than he got the theory of gravity right. It's just that he did something which was really quite unprecedented. And what does that theory do? It explains almost everything we need. It explains how you get from here to another planet. It explains how the tides work. But it doesn't explain certain things. For example, in that theory, if you suddenly pluck the sun away, we would immediately know that. We would not continue in our orbit around the sun. We would go off on a tangent. And well, that's kind of nasty. I mean, we don't know that anything acts right away. And gravity shouldn't do that either. In other words, it always takes some time when an action takes place and the result of the action. And in fact, in Einstein's world, it should take the time it takes light to go from here, from the sun, to the Earth, before we notice that, sort of 9 minutes later. And that is not part of Newton's theory. That's what makes up why you have to invent gravitational waves. That's one of the reasons. And so Einstein developed another theory, which is a theory which is very much more complicated than Newton's theory, but includes that. It includes the idea that there are new communication that you can do in and it does it by making gravity go away. There are no gravitational forces anymore. What exists in Einstein's theory is you put a mass into a system and it distorts the space. It really screws up the space. The geometry is no longer Euclidean. There's no longer 180 degrees in a triangle. It changes the angle. So it looks like, you'll see this when we talk about what a black hole does to space. I'll show you a picture of that. It's quite terrible. So it turns out that, and then it also changes the time. A clock, for example, that lives right close to us, let's see here on the Earth. And you put that clock up into, let's say, orbit around the Earth. You have to take cognizance of the fact that that clock goes at a slower rate. The tick-tock is slower on the Earth than it is when it's in space. If you didn't take that into account, you won't get home on your GPS. GPS has to account for that. And it's not inconsequential. Yeah, you'd land up, and not in the next town, but in the next block probably, something like that, if you didn't account for it. So what does the Einstein do? He changes space and and then the things that are in that space have to move in that curved new space. And that's the way he described gravity. So now I'm just going to tell you, I'm not going to tell you any more about it, but in that theory is gravitational waves. And what you're seeing on the screen is a gravitational wave, which I'll in a minute set into motion. But first, let me tell you what generates gravitational waves. It's very much like the same thing that generates electromagnetic waves. Many of you who have studied some physics know that you get electromagnetic waves from moving, accelerating charge. Well, you get gravitational waves from accelerating mass. But not every motion causes it. It has to be non-spherically symmetric motion. In other words, two things that smash into each other, that makes gravitational waves. Two things that go around each other, that makes gravitational waves. But something like a nice, uniform balloon motion where everything compacts together, that does not make gravitational waves. So that's what that means. And that's a specific property of the solution. Now, what do the waves, how do the waves actually work? The kinematics of the waves, how do they move and what do they do? Well, Einstein guessed they move at the velocity of light. That's what he guessed. And he turns out, typical of Einstein, his guts were better than his brain. He was absolutely on the mark. It was perfect. And you will learn in this talk that light and gravitational waves move exactly the same speed. We now know that from experiment. But he guessed at it. And then how does the wave do its stuff? Well, it's a transverse wave. It's a wave that we will set in motion in a minute with all those dots. Think of those dots as little masses, and I will start that interacting with the gravitational wave in a minute. But think of the wave, a transverse wave is a wave where if the wave is coming out of that plane, which is the plane you're seeing here, what it does is in this case, stretches space in one dimension, transverse to the direction of the motion of the wave. And then as you'll see in a second, it contracts space. So let's get this started instead of me just waving my arms around. So here you are standing right here where there's that red square. I hope you can see that. And I will try to make this go. And let's see. The way I can make it go is let's try this first. Yeah, good. It's a little bit slow because of the bandwidth of the system. That tells me the bandwidth of your system. Okay. But I hope you can see the motion. It's a little ragged. But at the red dot, nothing happens. At the red square, where I asked you to look first, right there. Nothing's going on there. But if you look in, let's say, the x direction, you'll notice there's expansion. But simultaneously, when there's expansion in the x direction, there's contraction in the y direction. You have to see that, otherwise you won't understand the detector. Okay? So the other thing that's in this thing is that the amount of motion for masses or these objects that are very far from each other, like the one way at the edge right there, that one and that one, that's a large, they have a large motion, those two. But if you look at the ones near you, right there, they don't move as much. You notice? And that is, there's a name for that. That's called the strain. In other words, the ratio in that picture at any one moment, at either the x direction or the y direction, the strain, the amount of motion, that's something, the separation between things changes. The change in the separation depends on how far they are apart. The further they are apart, the more change in separation there is. So delta L divided by L is at any one moment in that picture, positive or negative, but constant in X or Y. That have different signs. It'll be minus in one and positive in the other. So what does that tell you? If you want to measure these waves, you want to get a device that does the following. You want to get a device that measures strains that are different sign in two orthogonal directions. That's what you want. And actually, if you make the device bigger and bigger, you make it easier and easier to measure, because the amount of motion you have to measure is bigger and bigger. And as soon as you got that, you got the whole idea of how the detector works. Let me show you how the detector works, okay? So, but there's some tricky stuff here. Okay, let's see. Now here I want to advance the thing this way. Yeah, okay, now this is a setup in which a gravitational wave will be coming down on this plane, okay? And here, and the dots that I just showed you are in the plane, in this plane, the blue plane. And here is a laser. Of course, it doesn't look like a laser, but that will look a little better in a minute. This is an animation as well. The light will come out of the laser, hit this beam splitter, which is a device where half the light gets reflected, and that'll get reflected to that mirror. Half of the light will go through the beam splitter and hit that mirror, and then come back to this. And then the same splitting takes place again. And here is the photodetector. That doesn't look like a photodetector at all, but leave it go. Here is a photodetector. And let's get this thing running, and you'll see right away what happens. Wherever there's red, there's light power. Like, think of a red laser. And that wiggly thing you see is the electric field in the light. We have to take track of that. And you'll notice now, if you make the two paths between the beam splitter and one of the mirrors the same, you get no light to the detector at all. You'll notice that the light cancels. No light goes to the detector. If a gravitational wave comes along and moves the mirrors in that anti-symmetric motion, there will be light to the photodetector when the paths are no longer equal between the beam splitter and those mirrors. You get the idea? I hope you get the idea. Yes? No, if you say no, I'll do better. Okay. That is the fundamental idea of the device. It's really an extremely simple device. It's called an interferometer. And the idea was invented by a lot of people invented interferometers. And it's using light, timing light as a way of measuring distance. The time it takes light to go at a certain distance is an ancient art. It's the art, and that's the basis of the whole idea. Now comes the sticking point. And here's the guy who made the sticking point. Well, a lot of people, but this guy's most important for making the sticking point. That's Kit Thorne as a young man. And he doesn't look that way anymore. He's like me. We don't have hair anymore and a whole bunch of stuff. And but he was a guy at a group. He was at Caltech, and he was thinking about gravitational waves for years at Caltech. He had a group thinking about them, and he came to the conclusion that if you were going to try to measure gravitational waves, you had to somehow. You knew that you could do it with things on the Earth. That will be quite evident to you as we go along. You can't make a thing do that easily on the Earth. You just don't have big enough masses. You can't move them fast enough. There just isn't enough energy in the system to do it. It's just a scaling of numbers. The numbers are just too hard to make. But, and you'll see this as we go on, that's the whole problem. So H is, the measure H is that strain. And that's another way of saying the change in length divided by the separation. And here comes the sticking point. The sticking and stinking point. You've got to be able, if you want to measure something that is coming from gravitational waves anywhere in the universe, you have to be able to get at least down to the point where you're measuring strains that are smaller than 10 to the minus 21. And that is a number that was so daunting, even to Einstein. Einstein said, gravitational waves will never play a role in science. When he did his own predictions of these waves, of course, the technology was very different. There were no lasers, there was no electronics, but he couldn't imagine. I could imagine he probably sat down. I've asked the people who have the Einstein papers to send me or send the world the back of the envelope calculation he must have made to make that statement. All you have is a very bland statement in a paper he wrote. This will never have a role in physics. But he must have thought of things smashing together, probably trains smashing together. That's the biggest thing he could think of. And that makes a strain of 10 to the minus 45. I mean, even two trains on the Earth smashing together. Yeah, it's completely unheard of. You can't do it. He might have thought of two stars that are going around each other. And then people knew about two stars going around each other even in 1916, 1918. And to see a change in that, it would take the age of the universe to see a change in the things that he could see. So it was absolutely impossible. But anyway, let's go to modern days. And modern days, well, people began to think it might be possible. So if you make something that's 4 kilometers long and put that in there and multiply 4 kilometers by 10 to the minus 21, you get a number that is bigger, but just think about it. It's 4 times 10 to the minus 18 meters. Now, what do you know that's that small? Nothing. I mean, the size of an atom is 10 to the minus 10 meters. Of some, even a small atom, maybe a bigger atom, 10 to the minus 9, but that's it. Okay? So you're talking about the size of a nucleus. No, you're not. It's smaller than this. A nucleus is 10 to the minus, it's 1,000 times smaller than the size of the atom. So, you're 10 to the minus 13, 10 to the minus 12. And so you're talking about something like 1 part in 10 to the 5 of the size of a nucleus, or 1 part in 1,000 of a nucleus. And that's this 10 to the minus 18. And that is what, when you start proposing that to people, they say you're out of your mind. Okay, you talk to a mechanical engineer, and he just, or she does, she looks at you and you says, yeah, hey, nice kid, get out of here. That kind of. So let me put it into proper perspective so you have an idea about it. What does it really mean? It means that if you use light, you have to take somehow a light which has a wavelength of 10 to the minus 6 meters and divide it by 10 to the 12 parts. You have to somehow divide it like a ruler into 10 to the 12 parts, a million times smaller. Or, that turned out to be moderately easy. But this is the one that really took a long time. Even you and I sitting in this room, and I think here I probably could say this with a certain amount of sincerity, the whole place here, you may not realize it, is shaking like crazy. And it's not because you have apparatus in the other room. The Earth itself is jiggling up and down at hertz, at 1 hertz, which is typically by about a micron, 10 minus 6. So you're talking about wherever you are on the Earth, you have to get rid of the isolation, you have to isolate those mirrors that are going to reflect this by a part in 10 to the 12. And that turned out to be the hard part, as you will see in a minute. So yes, this was a big technology development program. That's what it was. And many universities wouldn't touch it, and MIT barely touched it. Caltech embraced it. That's the whole reason we were able. Caltech was crazy enough to jump into this. They said, yeah, we're not so scared of this. MIT was willing to tolerate it, but it wasn't going to go along with it until it became successful. Then they embraced it, but that's their own fault. Okay. So anyway, here, I won't describe all of this, but here is the way it's done, and you can ask me questions about it. I don't want to take a lot of time with this. But what is in here is, so you can see, here's what you had in that animation. There's the laser, there's that beam splitter, there's that far mirror, there's the other far mirror, and you add a lot of little bits to it. You make it so that you add some mirrors, like this one. It's a partial mirror, makes the light bounce back and forth about 300 times, and do that in both arms. Then, since all the light, no light is going to the photodetector, it's all going back to the laser. Well, you don't want that. The laser hates that. So you put another mirror in here, so you interferometrically cancel the light from the laser that's coming with from the laser with the light that's coming back from the interferometer. So that makes it so there's no light reflected from this mirror back to the laser. And then finally, there's another thing which you could use to tune the interferometer. So this is a way you get part of the way on that 10 to the 12. You make a much more complicated interferometer. And I won't say any more than to say the following. There might be 50 watts of light in this laser. There might be, in this little cavity in here, there might be something like 10,000 watts of light that's been built up. And in here, you might have a megawatt of light. That's the way this works. Let's go on. You can ask me about it later. Otherwise, we'll be here all day. So here are the different gravitational wave antennas that exist in the world of this style. The Americans built the first. There's one in Pacific Northwest. There's another one in Louisiana. And then there's one that came much later, but became very important, is one in Italy, near Pisa. And there was a research interferometer in Germany, which helped with a lot of in developing a lot of the technology. Now there's also one in Japan. That's about 3 meters. These are 4 kilometers, 4 kilometers. That's 3 kilometers. That one's 3 kilometers. And India is building one that's about 4 kilometers. And that is, but right now, why? Two reasons. You'll find out why you need many detectors. If you want to do astronomy, you need many detectors. I'll explain that to you in a minute. But the big thing right now, the ones that are operating at sensitivity that's good enough are only these three. All right, so let me show you a little bit about what the places look like. Again, I will go forward. Yeah, here's a little travel log. This is looking at the detector in Louisiana, looking at it from above. And I hope this works. Yeah, this is looking down on the one in the Pacific Northwest. And you can see these 4-kilometer arms that are inside. The vacuum system that's inside is in these concrete covers. These are the two places. There's the vacuum system. That's what you guys would be involved with. And here's a standard laser table, like at any place who's doing people doing laser research. And here's the control room in Louisiana. And here are people learning how to run the device. It's not so easy to run this thing. So, but you can train people to do that. So there you are. And here is sort of, I won't dwell on this except as a visual. Think of this as a thing not to understand completely, okay? But it's a picture of the sensitivity of the instrument, which gets better and better as you go down. As on the y-axis, you go down, the sensitivity is getting smaller. It's getting better and better. You're measuring 10 to the minus 19 meters per root hertz here, and here's frequency. For example, here's 100 hertz. Right about there is middle C on the piano, right about there. And this is a history from 2001 to 2006 of us, all those people working on that detector. And you can see it went many, 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 many orders of magnitude until we got down to here in about 2006. And we made design sensitivity. And there it is. And there in the dashed part is the design sensitivity. We did not make it at low frequencies, but we didn't miss terribly. But from about 70 hertz up, we made it. And that was two important things that came with that. One was, well, we knew we hadn't seen gravitational waves. We could say to everybody, we have a no detection, but it's a good no detection, not a foolish, no make-believe no detection. We are sure there are no gravitational waves at that level. That's a statement. That's a worthwhile statement. But the other thing is it proved that we were at least moderately confident to get this much of it working. And all we needed was how to get the rest of it going. And so the people who sponsored us, the National Science Foundation, said, okay, we'll give you another 150 million. By this time, we're into it already by 150 million. That was a big, big project for the National Science Foundation. And what came of that is the first changes were made. Here are the two changes that were made. I won't detail, you could ask me about it. One way is how you get the ground ice. At low frequencies, the important part was how do you isolate these mirrors better from the motion of the ground. That was the big problem. And so one way to do that is make a whole bunch of pendulums. Think of this spring attached to the ground, right? Well, it's somehow attached to the ground. And here's the first pendulum. That's one pendulum. Then you take another pendulum and add that, just hang it for the second one. Then have a third pendulum. And then you add a fourth pendulum. And here's this precious mirror that is supposed to not move at all, except from gravitational waves. And then here are fibers. And you may yet get to see these fibers in another mode. We were talking about it yesterday. These are quartz true silica fibers that are very, very, very low mechanical loss fibers. And so this mirror does not move much with Brownian motion from the fibers, thermal modes. I won't go into this picture, but it tells you that we are pretty much limited now by what's called quantum noise. The noise, the fact that the light is quantized. That turned out we're now limited by that, but we have ways that we can get around that too. And so let me take you right away to the next, because we're going to run out of time. And this is the discovery. The discovery was made as soon as we put those two things into the system and we got them commissioned, we began to see this. This was, I mean, it was very exciting. And this is about September of 2015. Now you heard about it in February of 2016. And I'll show you why it took a while before you heard about it. But this is what was seen. Here we are in, you can make it out. So here's living, this is time, and this is amplitude of strain. And you can see 10 to the minus 21. Kip was not too far off. And this is junk, that's all junk. And here something builds up. And here it's pretty strong, and this is junk again. And the same thing happened at Hanford. This is now the Pacific Northwest. And now let's superpose them. You can see how they sit on top of each other. So let me do that. Let me do that. Yeah, because they sit on it. There's noise. I mean, this is junk. but they're not identical, but they're identical enough so that you could believe that as being two signals that are the same. But what had to be done to make them identical was to take the signal from Louisiana, or the signal the signal from Pacific Northwest, and slide it back in time by about 7,000ths of a second. Why? Because it takes something like that long for the gravitational wave to go through the Earth from Louisiana up to Pacific Northwest. So that told us a couple of things. It told us whatever this source was, if it was a gravitational wave, it was from the south. That's why you need many detectors. That's the only way you can tell where the source is. It's by the timing of the signals. And the other thing it told you is that, well, it's hard to think of something that makes something 7 milliseconds different between the two places. But that was our problem. How do we know this is a gravitational wave? So let's go on. So you spent a lot of time thinking about this and looking at the data. And let's look at the next one. This is another way of expressing the same data. In this case, you're talking about time again is on the bottom axis, time from here to there. But this time, instead of amplitude, you're talking about the frequency of the sine waves that are needed to make up this waveform, which is the waveform we were just talking about. And I'm having trouble getting on that. There, I got it. That waveform, you've seen that already. And this little thing right there tells you the strength of, let's say here is middle C again, 256 right there. And that tells you, yeah, you got a lot of 256 in this, but not so much 32 hertz. And so now this is the sound. We'll listen to the sound this makes. And that will be the, let's see if you can hear this. That background roar is the noise, but every once in a while you go, oh, like that. Well, we'll speed that up a little bit, hear a little better. Okay, that's a chirp. It's changing frequency, and that was the giveaway. So now, what was this? And oh boy, all right, yeah, well, yeah. This is now the other big development that was going on simultaneously was people were learning how to calculate Einstein's equations on computers. It's called numerical relativity. It was a very important component to this. You could not solve these equations. But here's what, if you made a model, and this what you're about to see is the output of a computer. It's not an artist's rendition of two black holes. And people knew black holes should exist. We knew a little bit about black holes from the X-ray astronomers, but nobody was sure how many there were in the universe. And all of a sudden, we're seeing two black holes. Here, there are two black holes. And down below is space, which was flat. And you could see the holes that had been made in space, the curvature of space is in that picture. And the colors tell you how the time has changed. Wherever it's green, the clock's keeping same time. But where it's black, the clocks have stopped. And if you get, as these things get closer and closer, the collision of these two black holes, you'll notice you'll eventually build mountains into space. It's sort of getting more and more exciting. Then they slow it down. And the distortion of space there, the clock has stopped in the middle of that black hole. And it's a completely crazy place. Time has gone to halt. And now we have a new black hole. These two guys have joined. They've made these mountains in space, and they've caused the clocks to go crazy. And now they're the things that's going away from them are the gravitational waves. And that's what they claim, this model claims we will see, okay? So now, that's it. And what you do is we found out, and here is sort of the things we found out. We found out, for example, this is the waveform that we saw, that we've been talking about. And a little bit later, what did it correspond to, by the way? It corresponded, it corresponded to these black holes had a mass of 36 times the mass of the sun, one of them. The other one was 29 masses of the sun, and 3 masses of the sun disappeared in the gravitational waves, just went off. And for a moment, for some fraction of some number of milliseconds, this thing was the most powerful thing in the universe in terms of energy going out of the universe, brighter than in gravitational waves than anything else. All the light, everything, you could gather everything together. There's a huge amount of energy in this gravitational waves. And now the interesting thing about it is this here, I want to dwell on this only because it tells you something very important. If you took the same collision and put it at the sun, take those two black holes, put it at the position of the sun, what would you feel? What would you feel as the strain inside you? Well, it turns out nothing. You'd only feel about 10 to the minus 6 strain. That means your length would have been increased by a millionth, less than a hair. You wouldn't even know it. And you might hear it in your ear as a little click, that's all. Your ears are sensitive to just about thermal noise. And how much energy was going through you is unbelievable. 10 to the 25 watts per meter squared is going through you out of gravitational waves, and you didn't feel anything. Now, typically when you get a sunburn and you're sitting in the sun, you get a kilowatt per meter squared going at you. So this is 10 to the 22 times more power than what is coming out of the sun in electromagnetic waves. And that tells you, you get nothing. You get hardly any response in other words, what it tells you is space is very, very stiff. You can't compress space. In fact, space is stiffer than steel by 10 to the 20. It's just very, very hard to compress space. And that's what Einstein realized when he first ran into this. So it's very, I mean, people now say, oh, we should make gravitational waves on the Earth. Well, I wish you luck, that's all. Okay? So anyway, let's go on. What happened is that this happened, we got this notation, September 14th, 2015. Then we had another one, which none of us believed. That's why we don't have a GW for it. But now we know it's a real one, a little bit later. And then we saw one we did believe on Christmas, day after Christmas of 2015. And that one we believed enough so that we began to think, okay, this might be real. And we began to think of publishing it. But there were a lot of steps between us and publishing it. First thing we thought is this was something we had injected ourselves. The apparatus did this kind of thing on its own. We had to be sure that, and then we've been hacked. One of the very important people in our project is a guy named Matt Evans. He spent 6 weeks with a team of people establishing that we had not been hacked by outside people. And we never were able to come to complete certainty that we had not been hacked. Okay? And we'll come, there's ways of getting to that. So anyway, that was sort of the beginning of that. Those are all black hole events with different masses and spins and stuff like that. So the field was going. We published it. A little bit after that, a very important event happened. Virgo, this is that the detector in Italy, came on. And they were also able to see it. But now this is in 2017. And they saw signals like ours. They were not quite as good, but that's important. But what allowed us to do then is locate on the sky where the source really was. And we knew now that this thing was somewhere 1 billion light years away. We knew that from solving the Einstein equation. And here is sort of the area on the sky where if you only had LIGO alone, you would only have this big banana here. But if you added Virgo to it, because you had more separate time differences, you got something where this might be 1,000 square degrees of uncertainty. This might be only 30. And that made it possible to tell an astronomer, go look. And the astronomers would look at you and say, no, we don't deal with 30-degree uncertainties. So we had to do better, but still they tried. They saw nothing. Okay? Anyway, so that's the beginning of we'll call it the beginning of astronomy. Now there was another event that really was quite dramatic.
Yeah, you can ask a question.
Sorry.
I have a question.
Yeah, please.
So these waves traveled billions of light years to reach Earth. But during that time, nothing get attenuated?
They don't get, because they don't interact worth a damn.
So
they simply do not interact.
So the intensity never decreases?
No, the intensity increases like 1 over the distance squared. The field goes down as 1 over the distance. And we're measuring the field, the strain. But the power in the wave goes down as 1 over the distance squared. That's still true, just like it is for light. But look, these are, you have to live with that. But these fields, these gravitational waves continue on. They do not scatter from anything because you can hardly make them. And when they excite something, they hardly make anything move. So it turns out they allow you, and you've hit a very important point. You've hit the point why this allows you to do cosmology. It allows you to look all the way back to the beginning of time. If we ever get to that point, and we need more detection, we need more sensitivity to do that. But there's no reason we shouldn't be able to see the moment, the instant the universe got made.
So is there a limit on how far? There's no limit on distance? So how far?
No, well, the limit is how sensitive the detector is.
Okay, but in theory?
No, they're nothing attenuate. No, they will go on forever. They fill the universe up. Oh, yeah. No, they're not like light. Why does light attenuate? Because it's scattered by matter that's on the way. This stuff does not get scattered. Now we have another material of that, like neutrinos. They don't get scattered much either. That's one of the particles of nuclear physics. And that, everybody always thought that was the most penetrating particle in the world. The graviton, this gravity wave, is the most penetrating thing in the world. So it has this promise of letting you look everywhere. Well, and that is the real promise it has. Okay. So anyway, but you asked a very good question. Thank you. And so anyway, let me give you this. I'm going to get into trouble. Am I in trouble yet? Not yet?
Great.
Okay.
Plenty of time.
All right. I don't want to get into trouble with you guys, but anyway, so here is another source which has a, now that you're familiar a little bit with how this looks. This is, I'm not going to show you the waveform, but you'll hear it. But this is a completely different thing. Here, where the first one lasted by 0.2 seconds or something like that. This is a picture of frequency versus a time. And the color tells you how strong it is. And it makes a very long arc in here. Let me play it for you. I hope I can do it. It starts at very low frequencies. Anyway, I don't know if you couldn't hear the low, you need more amplitude to do that. But this is a real chirp, and it's a whole song, okay? It runs like a glissando on the piano, like this. And what was this? Well, it turns out we weren't the only ones that saw that. We heard it, in fact, there's quotes on it. We saw this. But right at the end of it, it turns out up here is a gamma ray telescope that's in space. And the gamma ray telescope, which actually saw it best, was something called Fermi. And the band that saw it best was the one that had a sensitivity between 50 to 300 keV. And here, look at that. About something like 1.7 seconds after the end of this thing, they saw a big burst like that. And another satellite, which is also another X-ray satellite, gamma ray satellite, saw it also. And this is another one in the same first one. Let's not get too detailed. A gamma ray satellite saw this thing a little bit later than we did. And now this, we know this source where that is. It's 140 million light years away from us. Why? Because we know from the amplitude and the masses, you get that all from solving the Einstein equations. You know that these are all about a solar mass. And they are, once you know that, you put it in the Einstein equations, tell you how much strain should you see at the Earth. And we saw so much, that tells you the distance. And we know then, we can tell if you have, that's the beginning of the story. We can tell people the distance and the strength of the device. And now other people, if they get told, and this is what happened, and this is why it's so important that there was a third detector. LIGO alone could give you uncertainty on the sky. That was this banana and that banana down here. So it's bad. But luckily, because Virgo is now on the air and we knew it should have seen this, it didn't see it. But that was a complicated reason. It didn't see it, but it should have seen it. It was sensitive to see it. What it means is that it was in a place in the sky where the detector had a minimum in sensitivity. That's all. And so using that piece of information, that allowed us to get the thing into a much smaller little thing. And then people then, sort of 10 hours later after we made the discovery, people saw an interesting situation in a region around this galaxy right there. That's a galaxy. That's outside of our galaxy. There is a new little pimple right here, that thing, and where the two lines are. That wasn't there before. Here's that galaxy 20 days before. And there are those two lines, there's nothing there. They're these stars, the stars in our own galaxy. They are just between us and that distant galaxy. So there was an astrophysical discovery that was something brand new. And it was right in the error circle of where the two detectors, or the three detectors said it should be. And my God, what science came out of that. It was wonderful. What it turns out to be was these two, this is a picture of what it is. It was two neutron stars colliding with each other. Now, neutron stars, I won't go into more to say that they have the mass of the sun, and they're made entirely of the inside of atoms, nucleus of atoms. So they weigh unbelievable. If you take a spoonful of neutron material, it weighs 10 to the 13 grams, one spoonful. You couldn't lift it. It's you're out of here, you bend the spoon. You couldn't do it. I mean, it's just the densest thing in the world. And anyway, so these two guys, when they collide, they eventually wind up making a black hole. But before they do that, they make all sorts of shenanigans. They make what's called a kilonova, very bright little spot that's full of nuclear energy that's driving the collisions of these neutrons into each other and into making protons and making elements. And so here's what's going on there. And this is something that I think you'll appreciate. This is a periodic table that many of you, as you're chemists more than I am, so you know all about this. Here is, it has a color coding, which you don't normally get. But here's hydrogen. And here is helium over here. And the color coding for this one is that helium and hydrogen are all made in the initial universe, in the explosion that made the universe. You don't need stars. They make a little more helium later on, but you don't need stars to make helium. And so you can see that you get helium, you get a little tiny amount of lithium, very little bit of lithium is made in the initial explosion. But most of the rest of the periodic table, until you get to the middle of it, is made by the cooking inside of stars. All the stuff we live with and we are part of, where it's made in stars and cooked in the star. Our sun is cooking up that periodic table right now. And it's all the stars sort of, when you look at them, begin with mostly hydrogen and helium. But there's a little bit of sprinkled other stuff in it that's necessary. And that sprinkled stuff is, of course, what makes life. Now, the thing that was harder for people to get was how you make very heavy elements. Our periodic table down here. And you'll notice that people had a lot of trouble figuring out how you cooked up. The stars didn't last long enough to make the very heavy elements. And it turns out now we know something which people had guessed at. They thought maybe the collision of neutron stars was the thing that made the heavy elements. And I think now we know that by looking at the light curve that the astronomers measured. So if you want to mine gold and platinum, you want to get yourself a rocket and go to the place where the neutron star was made into a black hole. You will find gobs of, you'll find the universe's supply of all these wonderful precious things is distributed all over wherever there was a neutron star. That's something we guessed at, now we know for sure. So that's the little hint. Okay, so I think we're almost at the end. I'm sorry I took longer, but we're not quite there yet. So let me do this again. And here's what we're heading for. And this is where we get to talk about where SilcoTek gets into this. Here is a curve that I won't describe any more than to say, this is a thing of sensitivity in the Y direction and frequency again. You should be getting slightly familiar with these. But this time we're showing the sensitivity of detectors. And the detector whose sensitivity is given by the very top here is the one that made the detections we just talked about. And we're planning a detector that is, right now we're building a detector that will be somewhat better, maybe 2 or 3 times better. That's called A+. And what we're hoping for is to get this field into a cosmology, which is to build a very much bigger detector, which is this thing here called Cosmic Explorer in the United States. The Europeans are thinking of building something called the Einstein Telescope, which is this is the 3rd generation gravitational wave detector. And you can see from this picture a little bit what that would imply. These colors that are in this picture, let's concentrate on the green and the purple. And you look at the first one, which is let's take the blue one, which we're going to be at. So here are the popular, this is now, in this picture, as you go out radially, is the distance from the Earth. It's also the shift of the lines. That we know that everything that's far away from us is moving faster than near us. So the further something is away from us, the more the frequency of it gets lower and lower, the wavelengths of it get stretched more and more. And that's called the redshift. And that was how we discovered that the universe was expanding. And now here is in this picture, which is sort of radial distribution of matter, here are all the black holes and that we think how they are. We're barely able, this line right there, this line with the dark, that first line right there is where we are with the sensitivity of the detector that we have. And you can see we should have seen some black holes, which we did. Here's this distribution of all the neutron stars. And here's again, maybe have seen a few. We've only seen 2. So there are far less neutron stars than there are black holes. But as you make better and better detectors, you can look deeper and deeper and deeper into the universe. And here, for example, if we build Cosmic Explorer and the Einstein Telescope, you should encompass every black hole that is in the universe, be able to get every one. And when they make binaries, the same thing here as with the binaries, with the neutron binaries. So this is a significant advance in the field and would let us look into the very early history of the universe. So that's the basis of, and here's what we have in mind. And the next piece of the talk is just about what we have in mind. This does not exist. Here's the artist's rendition of a 40-kilometer long gravitational wave detector put someplace in our country. And people look where they might be able to do that. And we find out we run into a lot of trouble with the fact that, not trouble, but we're going to have to talk to a lot of people to do this. Because this is a picture of the United States with all the indigenous tribes that own land. And it turns out the indigenous tribes that own land, we have to consult them all. But where would this be? There's lots of places where you can put an 40-kilometer detector in New Mexico, in Idaho, and in Utah. Those are the places where you find places where you can put a thing that's 40 kilometers on a side. And you then have to worry about all sorts of interesting problems. Over 40 kilometers, a straight line on the Earth is curved like this. And the light wants to go straight. So you're going to have to, by the middle of such a place, the light, you have to cut away 30 meters. 30 meters of, you have to make a 30-meter cord in that system. So anyway, there are lots of little problems, but the biggest problem is making it. And so here is the idea, so you can get the idea. This is very fanciful. So here we are in 2020, and we are thinking about it. That's called, these are studies of Cosmic Explorer. We're thinking of the design and how to do it all in this epoch from where we are now, 21, to about 28. We're not building anything yet, but all of this is design, research into trying to how to make this thing cheap enough. We'll talk about that in a second. And then here's construction that starts in the 30s and operation, we hope, by 35. That's sort of what we're imagining. That will never happen that way, but that's what is the imagination for this. And so here's where you come in. This is the last slide. So we're talking about an 80-kilometer, 40-foot diameter, ultra-high vacuum system. It doesn't generate a lot of gas of its own, except what it outgasses. There's nothing in it that makes, unless it leaks, then we're in trouble. Okay, we have had trouble with leaks in Louisiana. I won't go into that now. I think we'll have less trouble with leaks in places where there's less water. Okay, but nevertheless, that's the challenge. How do you make an 80-kilometer, 4-foot diameter, ultra-high vacuum system? If you take the costs based on our costs from LIGO, where we built 16 kilometers, 4 foot, 4 foot. I mean, 4 kilometers, 4 kilometers, 4 kilometers, and 4 kilometers. That's 16. And that, you're going 5 times bigger in terms of total tubing. That's about now, if you try to start building that in 2028, it would cost you just for the tubing alone and setting it up and getting it together, something like, I'll keep the precision, 680 million. We've done a fairly careful job of that. That's not the detector, it's just those tubes and getting them put in the ground. Okay, now, we think that if we can do certain things, we can change that factor by multiplying it by 0.7, or maybe if we're really lucky, down to half. And what are the steps that are involved in that? Well, one of them is to use carbon steel instead of 304 stainless. That's one place where you guys might help enormously. If you have SilcoTek outer coating to reduce the corrosion. There are other ways to do that. You can use epoxy. I'd rather use a silicone because it doesn't have a high, if it leaks, if there are little porous leaks in the tubing, we won't get hydrocarbons in if we use silicone. Silicone. That's one thing. So, but the more important one, that's one argument. It reduces the hydrogen turns out ordinary steel is less hydrogen, has less hydrogen in it than stainless steel. Stainless steel is full of hydrogen. And that's something that a good chemist probably can explain better than I can. There's a lot of voids inside stainless steel. There are hardly any voids for hydrogen in ordinary steel. We now know this for a fact. So we get that for free with but the water outgassing may be terrible. And we would like to avoid a in situ breakout. What we did in initial LIGO, we baked the whole tube by putting 2,000 amperes in the tube each one of those tubes got 2,000 amperes for a month, about. And we got the water out by getting it up to 150 C. That whole thing cost us $10 million. Here it would cost us something like 100 million. So I'd like to not do that. And last, so there again, if you could have a coating that is has less tendency to have water stick to it, and especially has less binding energy to stick to it, you could use the whole thing with a very much more gentle bake out. That's the important thing. So we think we could gain that, a good factor out of that. And we don't have to have a concrete cover. That was expensive. And oil burn, we would probably build the thing on like a railroad construction. That would be so what's required I mean, I don't know everything that's required, but clearly you have to somehow, the coatings to become part of the tubing fabrication process in some way. I now know what you guys are up against. And, you know, we couldn't take this process and immediately convert it into a mass scale without it costing more than the thing we're saving, okay? So that'll take some cunning. And the other thing I'm worried about, and you may have to tell me about, is how do you weld this stuff once it's been coated? I don't know that. That's another problem that we have to think about. So that's the end of the talk. Thank you.
All right. And
So, sorry, I took a little longer than I
oh,
said.
no, you're great. We've got all the time that we need.
Okay.
So if anybody had any questions, and anybody that's listening over the webinar, if you type your questions into the chat box, I'll be able to see them and I'll be able to ask them here. So if anybody has any questions, by all means.
Well, one of my questions and points is the purpose of the coating is to allow for a quicker pump down.
No, in this case, it's really money.
It's money.
No, it's real money because that bake out and the pump down would be really onerous with all that water.
Yeah.
No, if we can, for example, bake this at, let's say 50 C.
Right.
Instead of 150 C.
You get the relief.
Dramatic.
Yeah.
You know, and time as well. But time is less important because, you know, we're talking about here years of construction, years of running, and we don't open in our case, we don't do what an accelerator does. We would put, as we have, I didn't say this, but in LIGO, we have gate valves at the end of those tubes because we haven't actually ever had to put gas back into the tubes since the year 2000. We're holding on to a UHV vacuum for the last 20 years.
What is the vacuum level?
10 to the minus 9 torr, and the gas that dominates is hydrogen. That's the dominant gas. We have a little bit of water, but we baked the living crap out of that thing so that there's no water left. I mean, there was no water left.
What kind of pumps do you use to get that?
Oh, this was no. There was we have some ports along the way, and we had cryo pumps on ports that had 6,000 liters per second pumps. I mean, it took us a month, and we got the outgassing rate of water down to the point where it was sort of 10 to the minus 14 torr liters per second. Yeah, 12 liters per second per centimeter squared for water. And the hydrogen outgassing rate is about 10 to the minus 3 times 10 to the minus 14 centimeter, and that's the same, those same units. And that is the dominant gas load on the system. And that's also, thank God, the material that is least troublesome for the index of refraction fluctuations.
So gravitational waves and light travel at the same speed.
Yeah, to a part 10 to the 15. In other words, they're not just a little bit the same. They are identical. Think of it, over 140 million years on that neutron star collision. Those two beams have been traveling together for 140 million years, and they only arrive at different time by a little difference, like 1.7 seconds at the Earth. So those two things have to be the same when you do the arithmetic, to 1 part 10 to the 15 at least in velocity.
So is that like the universe's speed limit? Like
It's guaranteed the universe is limited. That was Einstein's story. You cannot do anything which transmits information faster than the velocity of light. And anybody who tells you about warp speed, tell them they're whistling with Dixie. You got to believe Einstein. You simply can't get around it.
So this strain, you calculate the strain.
Yeah.
Does it matter what events cause the gravitational wave? Is that strain always constant?
Oh, no. The strain depends on the accelerations. And from the waveform, you get a very beautiful picture of that thing that you saw doing this and all the wrinkles. and the spins interacting. And we will learn more about general relativity by looking carefully at the waveforms than anybody has ever been able to detect before. For example, I would love to know. I mean, a black hole is about the strangest thing that ever had been thought about. I mean, I don't know how much you know about black holes, but black holes are a place where nothing comes of it. You can't get out of it. You are stuck in a black hole. Your memory has been eliminated. You are gone. And you've been converted into either the mass, well, you've been converted to the mass of that object, but there's nothing left of you otherwise. No memory of anything. So what's left is mass of the black hole and the radius of the black hole. We were talking about this at dinner or something. And maybe if it's charged. And it turns out the black holes, so one of the questions that comes out of all this research is where the hell do they come from? Now, the black holes, most likely, when people began to think about black holes, and it was only in the mid-60s of the last century, about 1960, when people really began to see through work that, that Myron was part of, the X-ray astronomy people, they began to see stars that they knew in our own galaxy. They knew the stars, they knew all about them, but they were moving in some crazy way. They were moving, they were oscillating, but nobody could see anything that was accompanying them. So here's this star that they knew, and it's jiggling back and forth at some frequency. And you kept looking and looking and looking for something that was making it a binary. It couldn't find it. And so when they finally didn't know what happened, you can solve for the mass of the binary by a little bit of just simple Newtonian mechanics. And you find out, my God, the mass of the thing that they couldn't see was 4 or 5 solar masses sometimes, or maybe even some 10 solar masses. How can you miss a star like that? Well, they were missing them. They couldn't see them. And that was the first real discovery of black holes. And now now we see them copiously. And for some reason, they like each other. There's so many of them pairs. That's what we see. And so now, where do they come from? Well, they could come from stars that collapse. That's one way. But that's still a little spooky. There are too many of them. They could come from something called globular clusters, which are places in every galaxy where you have 10 to the 9 stars all together in one place. And they smash into each other and make black holes. And eventually there might be multiple body collisions. That's another way they could be made. And finally, there's a chance that they were made by the Big Bang itself, the initial part of the universe. Now, we have some limits on that. We know that it can't be all the mass because there's something called the dark matter in the universe, which is dominating the matter in the universe, something we can't see at all. But it can't be black holes. We know that for reasons of that if it was black holes that were doing it, big black holes, you would see fluctuations in that density of the dark matter. And we don't see that. In other words, if the thing is hundreds of mass solar black holes, I mean, right now we're seeing 150 solar mass black holes. That's the biggest ones we've seen. But our galaxy has a black hole right smack in the middle of it. That's 10 to the 6 solar masses. And virtually every galaxy in the universe has a black hole in the middle of it. So we never realized how important black holes are to the whole evolution of the universe. But now we know that. But those are other sources and may be seen by other techniques than what we're doing. In fact, there's a space technique, making a space detector that's going to see these big black holes. But never mind, that's a side issue. But so it turns out that we don't really know where these black holes come from. So we've opened up a whole field of let's figure out what the universe is really up to, And it turns out black holes, which look like they were a complete nut job, are a very much important part of the universe.
So we have a question coming in from people listening. They must be familiar with the light sails that people
build. The what sails?
Light sails out in
Oh, yeah. I know.
Is it possible to build a sail to ride a gravitational wave?
No. Oh, you're welcome to try it, but there's nothing there. You'll spend the rest of your life. You won't get enough gazookas.
So it just doesn't interact with matter.
It's just enough.
It goes through it.
It's just true. It goes right through it. And I'll tell you, you get a little bit of push from the gravitational wave, but look how hard it is to get that push. You see the push. So I would argue anybody trying to use gravitational waves for anything where they want to organize it has a hell of a challenge. I don't think I wouldn't put money into it. I wouldn't go near them. I think you're really stuck. I mean, I know there are people in the Pentagon who think, oh my God, we could communicate with gravitational waves and nobody would know about our communication with our whole subterranean submarine fleet. I mean, there are people I've talked to at the Pentagon and the Chinese, by the way, allegedly are way ahead of us on how to use gravitational waves to interact with their submarines. It's unbelievable crap.
Now, this is going to, I have no understanding.
No, don't worry about
I
it.
have no understanding of what dark matter really is.
Neither do I. I don't know what it is either.
So my question is there any way that these detectors, through inference or whatever, can they somehow eventually be applied
Yes,
to somehow prove or detect dark matter?
I think they can. And that's a matter of finding the right place in the universe and the right situation. I think we will learn something about dark matter from looking at gravitational radiation, especially, I'll tell you where it will happen. It depends how the black holes, I mean, that's where these careful measurements of the motion of these two black holes as they move together will be very important. And the more, as we go out, right now we're detecting a black hole, well, right now we were detecting a black hole event every week, one every week. With the improved detectors, which let's say you improve the detector by only a factor of 2 in sensitivity, you will get 8 times more black hole events. Why? Because you're looking twice as deep into the universe, but that goes as the cube of the volume goes as the cube. And so far, we're not yet in a place where we're saturating the distribution of black holes. So every time you increase a factor of 2, you're going to get 8 times more black hole signals. And that's what's going to happen. We're now going to get, in a set of event, one a week, we're going to get, 8 a week. And then when we build LIGO, if we build the GE, we're going to see an event every few minutes.
Right. Just
I mean, it's just
more data.
yeah. I mean, but the important thing is precision, and there's where it's so important that you have a good model. And thank God Einstein's equations. I mean, Einstein is, I don't know how he got so brilliant. I mean, it's just unbelievable. He seems to be right on top of it, even though he couldn't have done any of this. He would have known none of it. To me, it's just unbelievable how he did this. But the theory seems to work every time you challenge it. Every time people think they find a mistake in Einstein's theory, they find, no, there isn't a mistake. I don't know, you can't be that lucky forever, but at this point, we would use the Einstein theory and the computer solutions of those to look exactly for what you're asking. We would say, look, what's the cloud of dark matter that is accompanying the black hole? Because it wouldn't move with the black hole exactly. And you can see pictures of distributions of matter where a galaxy has sort of slipped itself with respect to the black hole. So you would get a different phase of the motion depending on, and the more precision you have, the more information you're going to get. So I feel quite confident we're going to learn something about dark matter. We may not learn what it is. We will learn how much and how dense it is and how clumpy it is. But we will probably not learn what the stuff is. That, by the way, is a wonderful challenge right now for all the people in science.
Fantastic.
I mean, a lot of the physicists that I know have converted themselves from particle physicists into people looking with fancy experiments at what might be the dark matter. And then the worst of it is something called the dark energy. We had a discussion about that yesterday, which was a discovery that was a lot later. The dark matter came from Vera Rubin and understanding galaxy formation and galaxy rotation. So that's an old story. And it's been woven into the cosmology of, we now believe it. But only about 10 years ago, people discovered that there was, besides that, something called a dark energy, which is, I mean, to me, completely wild. And that is the thing that is everywhere. And in fact, it has 70% of the energy density of the universe is in this completely wacko dark energy, which has one property. It's trying to push things apart. It's anti-gravity, sort of. And that, the dark matter makes up sort of 20% to 30% of the total mass of the universe. Remember, mass and energy are the same thing. They're still related by the velocity of light squared. I mean, they are the same object, whatever. Mass and energy are indistinguishable when you get to these things. And so you have most of the matter or energy is in, it's really energy, is in the dark energy, sort of 90% of it, or no, 80% of it. 20% of it is in dark matter, and I've now exhausted. 4% of it is in what we're made of. And that we can't understand, I mean, that we didn't know that. In your lifetime, my lifetime, we didn't know that when we were born. We thought the universe was all of the stuff we know. It's not. It's made up of stuff that we never even thought about. And that's all been discovered in the last, 30 years.
It becomes a comment more than a question, but we might even learn what isn't dark matter.
That's right.
That there are other things out there or potential.
Oh, yeah, you know, you're going to see, I'll tell you, general relativity must have new things in it that we haven't even thought about. And we will find that out. No, I think it's going to be an established branch of astronomy. And all the physicists who want to go into it have to become card-carrying astronomers. I mean, it's unfortunate, but that's, you know, I mean, there are a lot of card-carrying solid-state physicists, and they learn all this very specialized things. They almost look like chemists, you know. So I think there's going to be people who will think in grand scales, but other people who know all the facts, and they find a new fact, and they come up with something new that way. It's sort of fascinating that yeah, it's just another branch of astronomy now. I know that it's no longer was Einstein right or wrong, but we will find out where are there chinks in general relativity from this. And the thing that I keep saying that we will definitely find, but not, unfortunately, not with this detector, no other detector that you can imagine that I'm talking about here, the Cosmic Explorer, where it will tell you a lot about how the first stars got formed. And that's a deep mystery. And since you're chemists, you'll find out, try and make a star. I'll challenge you. Try to sit home and think how you would make a star out of hydrogen. Think about it. Turns out it's not easy because there's no states in hydrogen, ordinary hydrogen, that are low enough energy to emit, to damp the collisions of two hydrogen atoms. If you want to damp, take energy out of the collision of two hydrogen atoms, which is what's happening. To form a star, you have to get these two hydrogen atoms to slow down. And then finally get so slow they stick. So it turns out the only way you can possibly get that to happen, and imagine, it turns out through three body collisions. And that's so unlikely. Turns out, and then calculate that, and you'll be wondering, my God, how long should it take to make a star? You're still not there. It turns out the modern theory of making a star is beyond belief. You make, out of three body collisions, you make hydrogen molecules. Hydrogen molecules then lose energy through their rotation and vibration spectra. That takes forever. That's not dipole radiation, it's quadrupole radiation. So it turns out to make the first star is a real challenge for nature. And but here we are. Now, once you have the first star, you can make all sorts of other stuff, but we don't. And for example, James Webb, that new telescope that's going up, I think sometime this month.
This month, yeah.
Yeah, they hope to be able to see that process.
Oh, cool.
And we will have a lot to say about that process in gravity wave physics. So suddenly, you know, it's going to become more and more important. But my dream, and of course it's not going to happen in my lifetime, but for our successors, is that you can see the initial radiation that made the universe, the one moment when there was nothing and now there was something. That's our current visualization of how the universe started. It's completely wacky, but it seems to answer most of the questions that you have. Imagine that. You could make out of the vacuum, which is the vacuum is not empty. In modern physics, the vacuum is loaded with stuff. And the vacuum can make the universe. That's what the hope is. But when it does that, it makes a thing that expands and contracts, but expands very, very fast. That's called the inflationary theory of cosmology, which is a code word for something that's really crazy. The universe is a little bubble, and your oven, it suddenly gets formed. It expands in 10 to the minus 30 seconds to being to the size of, I don't know, a solar system. And then all of a sudden it's so hot, it gets very hot. It wasn't hot to start with. It was that gravitational dark energy that's pushing everything apart. And that becomes less important. And so the other gravity takes over, and everything heats up. And then the universe is on its way to becoming what we think it is. And then it has these density fluctuations that make gravitational waves all during that very first moment. And those would be gravitational waves that still propagate through the universe now. And measuring those would tell you exactly what happened at the beginning. Now, look, you say the end, I always think of the Hindus having a wonderful myth about cosmology. They have this great big thing full of milk, and the milk makes all these things and makes animals and makes everything. Yeah, I think the story is about the same. Okay. But it's based on what we know from the cosmic background and a whole bunch of things. So you guys got a very interesting future.
There's one more comment here. They said that Lisa Randall's work on dark matter, or what she calls transparent matter, is very accessible to go and explore online and read about.
Lisa Randall is a very good, worthwhile looking at. I'll tell you the thing I would look at is just look at the web. There's some very good stuff on the web, as you point out. This thing I was just talking about is sort of at the level of, and I'll tell you where it goes nuts. It goes nuts at a place where you don't know whether you want to go along with it or not. It says, there's more, if you can make a universe out of the vacuum, well, why can't you have many of them? And I can't answer that. Yeah, but they don't give you, the people who think that through, don't give you any way to try to detect that. And when you think about, no, there's no way of communicating one universe with the other. Well, then the hell with you. I don't care. I mean, if I can never establish this as a true fact and it stays part of the mythology, well, then, I don't care if you're right or wrong. You got to tell me how you could find that out. What other consequences does it have, you see? And this is called the multiverse. And that's where I parted with these guys. Anyway, don't ask me about the multiverse. I will give you nonsense. Any more on the set?
I don't see anything else coming through.
Okay.
So
people got tired. That's what happened.
Yeah, if we don't have any more questions, we'll go ahead and end the webinar there. And thank you so much for giving that talk.
Right, well, no. Thank you for having me. But I want you guys to think a little bit of how you might grow your process into something that could be used.